Welcome to Cal State East Bay's Data Science Club. My name is Randall, co-founder and president, and I'm excited you decided to join us for our official launch. To become a member, head over to our sign-up page by pointing your camera phone at the QR code in the corner, or click the link in the description below. Be sure to stick around to the end for an important announcement if you're ready to launch your data science career today. So let's get started. Most people are only vaguely familiar with the term data science. But if you've done a search of entry-level jobs lately, you'll have noticed at or near the top in terms of salary is a position called data scientist. We know these kinds of jobs require advanced computer skills and usually include people that work at big tech companies. But if you're like me, you'll have wondered, what exactly does a data scientist do? What types of skills do I need? And where do I get started? We'll get to the science part of data science in a moment, but let's take a closer look at the first part. What exactly is data? If the term data makes you think of modern storage devices like floppy disks, servers, or thumb drives that fit right in your pocket, you'd be correct. But the devices themselves are not data, rather the information that's been stored on them to be consumed or analyzed at a later date. Using that definition, we can see that data as a concept has been around a lot longer than we think. The first data was etched into stone, recorded as sheet music, and of course, inked onto paper. Slowly, what we now think of as data passed through many iterations over the years. First, we had programs that operated in terms of bits, like 8 and 16-bit gaming systems. The first floppy disks had memory in terms of kilobytes, CD-ROMs and DVDs, megabytes, and modern computing systems operate in terms of giga and terabytes. But as these technologies became household consumer products, the collective sum of the information being produced skyrocketed. Modern companies must now operate in terms of peta and exabytes to keep up with consumer demands. Let's attempt to put this into scope. Let's say that this is 1 exabyte, or about 1,000,000 1 terabyte hard drives. It is theorized that by 1997, all of the information ever created throughout human history, every Bible written, every Rembrandt painting, all of it converted into a digital form would exist on about 12 exabytes. For scale, that's a 12 with 18 zeros behind it. It's a lot of data, right? But this is dwarfed by today's standards. Estimates show that by the end of the year 2020, we would have produced 44 zettabytes, a 3,600% increase in about 23 years. What's more surprising is that a large majority of this data, about 90%, has been generated in the last 2 years alone. However, this is small fries as we look into the future. Projections show that by the year 2025, we would have produced 4 times this amount, or about 175 zettabytes. Pretty mind-blowing, right? If you feel these numbers are too big to wrap your head around, I'm right there with you. Hence the term, big data. So how do we measure big data? Big data is commonly characterized by the 4 V's. Big by volume, or the amount of storage space required for the data to exist. Big by velocity, the speed at which the information is produced and consumed. Big by variety, or the number of formats and structures data can come in. And big by veracity, or the range of certainty of the data's usefulness and accuracy. So, clearly we're swimming in a vast, limitless ocean of digital data, which begs a few more questions. Like, why do we have so much? Where is it coming from? And what do we do with it all? The media outlet Raconteur put together this infographic that might give us a clue. Let's take a closer look. Every 24 hours, 500 million messages are sent on the Twitter platform. A little less than 1/3 of a trillion emails are sent globally. A number that is expected to grow dramatically as emerging economies gain internet access. Machines like smart cars send terabytes of information collected through its many sensors, as well as wearable electronics collecting information while we sleep, work, and exercise. And then there's this, easily the most mind-blowing figure in this graphic. This projection says that inside of 5 years, our daily data creation will be in excess of 460 exabytes. That's equivalent to about 40 times the collective sum of information created by humanity up to 1997, every single day. If that doesn't blow your mind, I don't know what will. There's a lot more to this graphic if you want to take a closer look. I'll link to it in the description down below. So what happens to this information when it is tweeted out and emailed? Well, today it is collected by various companies and funneled into teams that have the tools to take a closer look. Teams of marketing analysts, business analysts, and other data professionals. So, with all these people working on it, this data will be processed in no time, right? Well, not quite. Turns out only about half of this data is structured or formatted for analysis, and only about 1% of this data will be analyzed at all. This means that for the foreseeable future, there will be more data than we know what to do with. It seems as though data is the future of business. The U.S. Bureau of Labor Statistics put out a report estimating that by 2026, we would have created 11 million new data jobs. And the private sector agrees. The media outlet New Vantage published their executive survey, in which 97.3% of Fortune 1000 companies that participated in the survey confirmed that they are investing between $50 million and $500 million in big data and artificial intelligence. Companies like Motorola, American Express, and NASDAQ, just to name a few. But the data science revolution is not limited to industries with traditional data skills. Professions like law practitioners, personal and business coaches, journalists, and those in the media industry, as well as educators, are using the powerful potential of tools like natural language processing to give them a competitive edge over those using legacy systems. But what are the traditional industries that use these data skills? Well, more commonly, those with data science skills have a background in one or more of the following areas: computer programming and information technology, those with strong math and statistics skills, and of course those with business domain knowledge and acumen are the ones who work on finding the value in raw data using tools like machine learning, traditional empirical modeling, along with new and cutting-edge software to tackle big data challenges. The nexus of these domains is where the data scientist operates. Let's take a closer look at how one enters each of these fields. If you're a student, you want to look at majors like computer science, information technology, and engineering to find work in roles like software engineer, data engineer, database management, and data security. In these roles, folks will develop skills that translate into other domains, skills like machine learning, creating specialized software to handle data science and big data engineering challenges. Another route would be for those talented in mathematics and statistics. This includes majoring in physics and engineering. When they go into roles like quantitative developer, machine learning engineer, and statistician, they will develop versatile skills like machine learning, quantitative analysis, as well as business analytics. Lastly, those pursuing a degree in business like business admin, economics, finance, and marketing will pursue data careers like business intelligence analyst, marketing analyst, financial and quantitative analysts, as well as IT management. They will develop skills needed to apply the machine learning to business cases, manage data flows, and optimize the tools designed for big data. As you can see, the field of data science includes more than data scientists. There are many specialized roles like business analyst, data engineer, and business intelligence analyst, the data scientists themselves, and the software developers that all work together to work on what's called the data science project lifecycle. The timeline starts with business analysts and accountants laying out a runway for funding the project. This is followed by the data collection and what's called the last mile ETL, or extraction, transformation, and loading of the data to be processed for the next stage. Next, engineers develop hypotheses and work on finding optimal features so that the data can be ready for the central part of this process. Next, a team of data scientists work on developing the right machine learning process to achieve the business's objectives and key results. This can include one or an ensemble of methods like data mining, or what's called natural language processing, like I mentioned earlier. More traditional tools like linear regression algorithms. Classification methods like regression trees and clustering. Or more modern tools like neural networks and deep learning. Finally, business analysts and engineers create powerful business intelligence tools like dashboards to monitor the process and get ready for production. Here, security features are added, and software engineers work on putting out any last-minute fires. This process, or something close to it, is what you can expect to work on should you find yourself in one of these roles. You might be saying, well, hold on a second. I don't know how to data. I'm not really good with computers. And what the heck is an algorithm? Don't worry, Data Science Club is here to help. Together, we can work on building these skills. We can start with the most common tool used for data analysis and manipulation, spreadsheets. We can use the tools available to us, like Microsoft Excel or Google Sheets, to help you learn this valuable skill that employers expect to see on your resume, implementing the formulas and navigating their click and drag features. Next, we can look at another essential data tool. Learning sequential query language, SQL for short, will give you the ability to query, sort, and port data stored on databases. Even if you've never written a line of code, this ultra-simple and repetitive query language will get you comfortable working on the command line in no time. Next, we get to the fun stuff. We can look at how to store this data locally so that we can load it into a virtual environment where we use the power of Python and its many libraries to process the data, write algorithms and programs to create various data structures and outputs. This is a great place to start if you're new to computer science. For those looking for another challenge, we can look at R. This language is specialized for dealing with numeric data, and the virtual environment, RStudio, gives us a wealth of powerful tools that can do anything from creating beautiful graphs and visuals to creating a detailed report or publishing to the web with a click of a mouse. This skill is an industry standard for those looking to fill a data role. Another essential skill is learning how to piece it all together to communicate it effectively to others. Data visualization using Tableau and Power BI is a must for anyone looking to get into the data science space. Along with services like Google Analytics, we can work on constructing powerful analytical tools, like dashboards, that are sure to impress. And of course, we'll do a deep dive into machine learning, looking at all the varieties we mentioned earlier, along with important points like a 5-step machine learning process and concepts like over and under fitting that you are sure to encounter in the future. If you're interested in machine learning, but don't yet know how to code, don't fret. Powerful machine learning tools like Google's AutoML and TensorFlow are made precisely for you. Now, if all this seems very elementary to you, I say perfect. We can dive into more challenging concepts like quantitative finance, focused on topics like time series forecasting, algorithmic trading, and fintech modeling. We can also look at data engineering, learn database design, data warehousing, and big data engineering tools like Databricks and Apache Spark. If you're up for it, you can also join Cal State East Bay's Data Science Workgroup. This group meets in person at 2 p.m. most Fridays. This can be a great place for you to put your data science skills to the test, working on teams and presenting your findings to the group. The skills you will build here will serve you well beyond the university level. By starting Data Science Club, we hope to develop future data science talent in all its forms. If you're not a student, or if you want to participate in this development, we invite you to lend us your knowledge and expertise as a contributor. By creating content for our club, you can be an integral part of growing our network. If you're interested in becoming a contributor, be sure to mention it when signing up. We will be happy to have you. And finally, before closing, I wanted to share that important announcement I mentioned earlier. We started Data Science Club not as a destination, but rather to serve as a grand central station on your data science journey. There is a plethora of online resources that will aid you in this journey, many of them free. One of these resources is called GitHub. It is an online repository for personal projects and is a must for anyone looking to showcase their digital talents. They have partnered with a company called DataCamp, which offers an online virtual environment for you to learn data science and analytics skills. As of the recording of this video, in late April 2020, if you sign up for a free student account with GitHub, DataCamp will give you 3 months of access to their platform absolutely free. Head over to GitHub now to sign up. I'll put the link in the description, and claim your 3 months of free data science training today. So join us as we make the next few months of 2020 the summer of data science. Head over to our membership page now to get started. Bye for now.